Okay, what we're going to do in Module 3 is we're going to be looking at some actual data and see how we can best summarize the data. In Module 3, the best fit that we're going to be looking at is a linear fit, a line. Now, if you look at Scatterplot 1, you could see that those actual data points are probably best not summarized by a line. A curve would be a better choice. What is a scatter plot? Well, a scatter plot sort of looks like your coordinate system. It has an x-axis and a y-axis, except the points that are plotted are actual data points, and they're not connected with a curve or a line. They're just loose points, and they represent actual values. And we want to try to see how can we summarize all of that data. And Module 3 looks at just using a straight line. Now, if you look at Scatterplot 5, that definitely doesn't seem like a line would do the trick. Neither does Scatterplot 3 look like a linear model is the answer. But Scatterplot 2, 4, and 6, a line would be the way to summarize that data. Now, notice in Scatterplot 2 and 6, as x gets bigger, y gets bigger. That's called a positive relationship. In Scatterplot 4, as x gets bigger, y gets smaller. That's called a negative relationship. The next thing we want to do is we want to look at how good of a fit a linear model or a line is. So we come up with something called the correlation coefficient. Now, if you have a positive relationship, the closer the R value is to 1, the better the linear fit. Now, let's look at Scatterplot 2. That has an R. R is the symbol for correlation coefficient. That has an R value of 1. That's a perfect linear fit in a positive relationship. If you look at Scatterplot 1, that has an R value of 0.943. Okay, so that's a little bit not as good of a fit, but it's still pretty close to 1. Okay, now if we were to look at Scatterplot 3, okay, even though I don't have it written down there, the R value for Scatterplot 3 is roughly about 0.5 or 0.6. It's not as good as Scatterplot 1 and 2, okay, but it's still not bad. So in other words, the less of a perfect line you have, the R value goes down from 1 closer to 0. Now let's look at Scatterplot 4. We can't tell if that's a positive or a negative linear relationship. The R value there is almost 0. Okay. If we go on to Scatterplot 5, that's a negative relationship. Okay. Again, a line is not a perfect fit. The R value is negative, a negative 0.449. And in Scatterplot 7, that's a perfect negative linear relationship. It forms a perfect straight line. The R value is negative 1. So the R values are always between negative 1 and positive. All right, now, when we have a line of best fit, what that means is it's the line that best summarizes the data. Now, you have some actual data values, okay? But we also want to look, what would the line predict? This line of best fit, what would the line predict the data value to be? Now we're going to be looking at an example here where we have X values pages of a book, of a textbook, Y values are the prices of the textbook. Now here we have a line of best fit that has the equation predicted price equals 0.15 times pages plus 42.32. We're going to look a little bit later on. Not only how do we get the line of best fit using our TI calculator, how do we also get the correlation coefficient? Now, in this equation here, the predicted Y value is always denoted by Y hat. The actual Y value, the actual data value is Y. So, instead of saying predicted price, we'll typically say Y hat. That's the predicted Y value. Instead of saying pages, we'll typically put the variable X. Now, if we wanted to know what would the line of best fit predict a textbook of 600 pages to be, X would be 600. You plug that into the formula, you get $132.32. Now, that's not the actual cost. That's the predicted cost from the line of best fit. Okay, so the next thing is, we're going to talk about how do you get a line of best fit. Now remember back in Module 2 when we were doing standard deviation, when we started summing up the deviations, do you remember that the deviations always added up to 0, so we had to square them? Well, there's something here called a residual. A residual is the difference between the dot, which is the actual price of the book, and the y value from the dot and the y value on the line. The y value on the line is your y hat value. That is the predicted price using the line of best fit. Now, a residual is the difference between actual data value y minus predicted data value y hat. So the residuals are these vertical lines here. If the point is above the line, it's a positive residual. If the point is below the line, it's a negative residual. Now, if we were to add up all the residuals for all of the data points, they would add up to 0, just like the deviations for standard deviation. So what do we do here? We square the residuals. The line of best fit is the one and only line that gives us the smallest value of the residuals squared, being summed up. Now, if we have a book that is 696 pages, the actual value of this book is $122. How do we get the predicted price? Well, here's our formula again. So it's 0.15 times the number of pages plus 4232, $146.72. The residual is the y value, the actual price of the book, minus the predicted price. Well, we were given the actual price of the book is $122 minus the predicted price. We just figured that out, $146.72. The residual is negative $24.72. And here you can see right here, this is the actual data point for the 696 page book. Up here is the y hat value on the line of best fit. When the data point is below the line of best fit, the residual is positive. When the data point is above the line of best fit, the residual is positive. Next, how do we use our TI to get not only the correlation coefficient, which will tell you how good of a linear fit it is, but also the line of best fit? So let's do this with some data points. X is 1, y is 4, x is 2, y is 5, x is 3, y is 9. We want to get the R value. We also want to get the line of best fit. The equation of a line is y equals ax plus b. A is the slope. Now what does slope mean? Slope means as x goes up by 1, how much does y go up or down by? If the slope is positive, as x goes up by 1, y is going up. If the slope is negative, as x goes up by 1, y comes down. Now b is the y-intercept. What does that mean? That is the value of y where the line hits the y-axis. What is the x value on the y-axis? It is always 0. Now I already entered the data values, but what you would do is you would come over to your TI-84. The x values go into your list 1. Now we're going to have to actually use two lists. When we did the 1var stats for the IQR and for the median, and we did the mean and the standard deviation, we only used one list, typically L1. So what we're going to do here is we're going to have list 1, L1 for the x values, L2 for the y values. So hit your stat button. So your stat button is right here. Edit, enter. Now I already entered the values. You would clear your list 1, clear your list 2. I entered the x values 1, 2, 3, and I entered the y values 4, 5, 9. Now the next thing we're going to do is we're going to hit stat again. We're going to go over to calc. Now this time we're going to go down to linreg, ax plus b. That's going to give us the linear regression line, also called the line of best fit. So you go to option 4, hit enter. Now you have to tell it what list. What are the x values in L1? What are the y values in L2? We're going to keep hitting enter. Okay, and notice I got my A and B. My A is 2.5. My B is 1. So the line of best fit, your y hat, equals 2.5x plus 1. So again, we're going to replace the A and the B with the particular numbers. So again, line of best fit in this case is 2.5x plus 1. Now, they gave us the R value, 0.9449. That is the correlation coefficient, which tells us those 3 points form a pretty good straight line. Not a perfect straight line, otherwise the R value would have been 1. It also gives us an R squared. Now we're going to look in a few minutes and see what the R squared means. Now just in case on your TI you don't get the R and the R squared lines, come down, you see 0 above it is catalog. You're going to hit the second button and then 0. So you're going to hit second and 0. You're going to keep scrolling down until you get to diagnostics on. So you're going to go down. And when you get to okay, so we hit diagnostic on, we hit enter again, done. Then your R and your R squared would show up. We saw in the calculator something called R squared. Now what does that tell us? Well, let's look at this picture. Here we have a data point. And notice that this thing called unexplained, that is unexplained deviation. Well, here we have the Y bar. That is the average price of a book. Now notice there's a deviation between right here, which is the predicted Y value for an 847 page book, and the mean of books. What causes the deviation between the predicted price of the book and the mean price of all those textbooks? Well, that deviation is explained by the number of pages. The number of pages affects the price. But notice the total deviation between the actual data price of the book and the mean not only has an explained piece, something called an unexplained piece. That's the portion of the deviation that is not told to us by the number of pages. The number of pages doesn't account for that. There's something else that accounts for this small deviation right over here. That's called unexplained. The number of pages doesn't tell us where that portion of the deviation comes from. Another word for unexplained deviation is residual. Residual, notice, is data value minus the predicted price of the book. And it so happens that if we look at all the points as a whole, all of the points, that the proportion of explained deviation, not just for one point, but for all the points, is R squared. And what did we happen to see in our calculator? It was the correlation coefficient squared. So again, R squared gives you the proportion of deviation explained by X, your explanatory variable, which in this case is number of pages. And finally, this is a bridge into Module 4, which looks at exponential models, no longer linear models. Let's look at this collection of data values. Now you notice it looks like a curve might do a better job of fitting that data. So yet they drew a line of best fit, but actually an exponential model would probably fit that a little bit better. How do you know if a line is not the best choice? You have something called the residual plot. Instead of having the Y values versus X, you form the residuals. And you plot the residuals versus X. If the residual plot forms a pattern, and in this case the pattern is, it looks like a U, then a linear model is not the best way of going. Another model, like an exponential, might be better.